If you've been watching my channel for a while, you know that I am absolutely obsessed with the European Space Agency's Gaia mission. This is this 10-year astrometry mission where this spacecraft is measuring the position, the motion, the chemicals of billions of stars in the Milky Way, building this really comprehensive 3D map of everything that's around us. And astronomers use this data for all kinds of incredible discoveries about in so many different aspects of astronomy, understanding the mergers and the motions of stars that are on escape velocities and our position within our arm of the galaxy. And it goes on and on and on. It's too much to say. But fairly recently, astronomers discovered in Gaia data a fairly massive black hole fairly close by us. They were able to see the sort of swirly motion of the star because of a large black hole that was nearby it. And this was covered widely in the news. We covered it in Space Bites. And after I posted Space Bites, one of the researchers who worked on that paper reached out and said, "Oh, do you want to talk some more about the discovery?" And I did, but I really just wanted to talk about Gaia. I have so many questions about Gaia. I want to understand more deeply how this amazing mission functions. And so I was able to conduct my dream interview about Gaia. So my guest is Dr. Berry Holl. He is a research associate at the University of Geneva. He's an astrophysicist, but specifically, he is a Gaia data specialist. And so he's one of the people who is working behind the scenes at all of this Gaia data and trying to normalize it, trying to weed out any kinds of problems with their system, with their data, and prepare these giant data packages for astronomers. And they're working on the 4th release, which is due at some point in the next year or so. And we talked about sort of the history of astrometry, how Gaia functions, and go into enormous detail about all of the instruments and exactly how this mission works and gets the kind of data that it does, what its limits are. And then, of course, what I like to do, what comes next? What are the kinds of missions that could follow on in Gaia's footsteps and give us even more data about the Milky Way, about stars and other, in other wavelengths that maybe we can't see with Gaia. So the one downside of this interview is we actually don't spend very much time on the black hole discovery at all. It's a black hole, it's kind of close by, found with Gaia. We talk about it a bit, but more it's about the mission itself. So enjoy this conversation with Dr. Berry Holl. Berry, when did you first get involved with the Gaia mission?
Well, that was actually when I started my PhD, which was in 2007. So I've been 18 years in Gaia. So I did my master's in Leiden, in Holland. I'm Dutch. And afterwards, I was looking for an interesting position. And there was something about Gaia. And it was not launched then yet. It was early stages. And I applied, and I never left, basically, because there's so much to do in the mission. That's basically it.
It's funny to me, like, my audience knows I'm absolutely fascinated with this mission. We have a bingo card that whenever I mention Gaia, then they choose it. And I think it's because I love the idea of surveys, of databases, of repositories of information that then astronomers who have some question can, instead of booking time on a telescope, look at thousands of examples of that thing. So, like, what was the goal with Gaia to try to pull together as much data as humanly possible?
Yeah, Gaia is a real survey mission. So we set out to basically map the galaxy. It sounds big, and it is big. So in principle, Gaia is observing about 2 billion stars, which is about 1% or so of the full galaxy. So that's a significant sample for astronomers, for sure. And the idea is basically to provide in multiple domains, and we can come back to that, in photometry, in radio velocity, and in astrometry. That was the main mission objective initially. A catalog of all these objects where people then can indeed do searches on whatever they are interested in. And so there goes a lot of effort into calibrating the raw data from the satellites and then producing, in that sense, different catalogs, which we then release in what we call data releases. So we had 3 up to now. The 4th one is coming in maybe 2 years or so.
Right.
Yeah.
And so let's talk about the process. So, I think, we're roughly familiar with this idea of astrometry, of photometry. You're measuring the movement, you're measuring the location and distance, you're measuring the changes in brightness and maybe even what's made of. But how does Gaia perform these functions with so much accuracy?
Yeah. Well, it's a technical feat, which is unmarveled, I would say, because if we look at the history of astrometry, so the measurements of stars, the position measurements, basically the instruments from Earth were sort of limited. They increased slowly still, but we have this atmosphere which is blocking us most of the time, and we need to do adaptive optics, etc. But if we want to make a global map of everything, we need to go to space. So the first mission that did this was Hipparcos, which was launched in 89 and was operational till 93. And it was basically a precursor of Gaia to do the same thing. But then, so Hipparcos actually made an improvement of about a factor of 100, and Gaia did another factor of 100. So we are measuring with Gaia, just to give you one of those ridiculous imagination numbers. If you look at a coin on the moon as seen from the Earth, that is the kind of final precision we can get on positions with Gaia for a large fraction of the stars, which is unprecedented. And with that, you can discover a lot of things, like if there's something going around it, like a planet or a black hole. And your question was, so what kind of processing and how does it work? So Gaia basically goes with the Earth around the sun. So if you have the sun, the Earth, and then you have actually a point, the Lagrange point 2, which is moving with the Earth around the sun. And Gaia basically looks away from the Earth and the moon, so it doesn't get blinded like some satellites that go around the Earth. So it basically has an unobstructed view of most of the sky all the time. And then it spins continuously every 6 hours, and it has 2 big telescopes, which are combined. And the combination of this wide angle and all this rotation, together with the motion around the sun, give you a pattern that we call it the nominal scanning law, which in the course of 5, or maybe now with extended mission 10 years, will give you a quite uniform distribution of observations on the sky. So every point is observed roughly 100 times over this time span. So we measure a position of the star at all these intervals, which has an interval of a cadence of maybe 2 to 4 to 6 hours, and then maybe 26 days, and then up to like 5 or 10 years. And by combining all this data, so it's very sparsely sampled as well. People are maybe used now to, for example, Kepler data, where you have observations of photometry which are very irregular, but we actually have very sparse data. So it's both a challenge because it's not easy, for example, to search for periodic signals in this kind of data. But on the other hand, it gives us a lot of information about all these stars. So we're trying to optimize this to harvest and get the most out of it.
So let's break these down piece by piece. So, Gaia is at the L2 point, as you said, it's orbiting around the Earth. So it's spending time on one side. It's orbiting around the sun. Yeah, it's orbiting around the sun. It's spending, it's on one side of the sun. It makes a series of observations. It's on the other side of the sun. It makes a series of observations on the same. So you've essentially planned out all the parts of the sky, and then there's like a schedule that when you're in this position, then these are the stars that you're checking from to build the parallax view. Yeah.
So in principle, it has 2 fields of view, as I said, which have an area of roughly the moon size as area, and the satellite is spinning, so it's going around every 6 hours. If you would leave it like that, it would just make a band on the sky of 0.7 degrees width. Now, due to the precession, there's a precession of the spin axis of the satellite. So the satellite actually is it's like a head structure. So the head, the backside, basically protects it from the sunlight, and behind there is a tent where the telescope sits, and it's always 45 degrees away from the sun. So it's always in the shade. The tent is behind here, and there is actually a specific motion that it rotates like this, and then also around the sun. And this combined motion gives you that in the course every half year you see at least every position on the sky, but it's basically sampling different parts of the sky continuously. So there is no scheduling as such. The specific thing also is that it has we call it a sky mapper. Everything that is brighter than a certain magnitude, which is now around 21 or so in G magnitude, it will observe and store in the database of online in satellites, and then later it gets downloaded and we try to make sense of this. So it is in that sense a blind survey. Anything that pops up, so also supernova, whatever might be there, it can pick up, and it actually has done this as well. So
and so then you're getting this continuous observation. You're pulling all this data back, and so we talked about the idea of say for the astrometry to find the positions of these the distance and location of these stars. Yeah. You're getting about a couple of observations per year for each one of these stars, and then same thing, like say with the photometry, you're getting a handful of observations of each star each year that then over the course of the full data set will then you'll be able to provide, say, 100 observations of this one star.
Yeah, that is correct. Yeah. And maybe just going a bit in the astrometry part of it, because the whole thing about astrometry is measuring the positions and distances to stars. So how do we do that? Because we basically use the motion of the satellite around the sun. So it goes 1 AU on one side and 1 AU on the other side. And just like with your two eyes, you can basically distinguish if you close or open one and something is close by or far away, it will seem displaced with respect to each other. And we use this 1 AU baseline on both sides to see how the stars move with respect to each other. And now this 1 AU is very small with respect to the size of our galaxy. So therefore, we need this ridiculous precision to actually, with this 1 AU, we can actually see the brightest stars on the other side of our galaxy wobble a little bit during the year. This is incredible if you think about it, but that's what we're doing with Gaia.
Yeah, I mean, the recommendation that I always make to people to wrap their mind around is to hold their arm out, put the thumb up, and then just open and close each eye, and you'll notice your thumb jumping back and forth. And so imagine each of your eyes is on either side of the sun, and your thumb is the foreground star, and the background is the background of the universe, and you're watching your thumb jump back and forth, and you can measure that, and you can calculate the distance to your thumb just by how far it moves back and forth. But it's not just the location. How do you get the speed and direction of the stars?
Yes, so as part of astrometry, we measure the position of stars repeatedly. So what do stars do on the sky? If we just look up, they look static, didn't move, but in principle, they all are moving, which we call proper motion, and many people are aware of this, of course. So in the course of time, some stars actually have quite a high proper motion, so you can see it over the years, several arc seconds or so, like Barnard's star is one of those examples, which you can actually, with your backyard telescope over the years, track the motion. So if you, to first order, everything of course revolves somewhere around in the galaxy, around the center, but we are having a very short time span. So to first order, things look to move linearly in space. So that is the proper motion. That's the first order model we make. And then by measuring over time the position of each star, we can see that, okay, there's a linear motion. Now, what we just were saying, that because due to the parallax, we are moving around the sun. So this star, from Gaia's perspective or our perspective, is not moving in a straight line, but actually it's making a wobble while it's moving. So it's going like that. So every year gives you a wobble, and this wobble is proportional to the parallax. So the further away, the smaller this wobble is. Now, if for most stars, this is basically the motion that we can see. And also, of course, somewhere in the middle of that time range that you have data, you put a position. So you define a reference time, and that gives you the position at that time. So now we have position, proper motion, and the distance encoded as parallax. But on top of that, many stars are not single. So we have a lot of binary stars, or things with a planet around, or a black hole. So there's an additional motion of this star on top of this motion that I just described. And this is, of course, where things become really interesting, and where we're trying to build catalogs specifically for these kind of components that might be going around. So, for example, I've been involved with the work on detecting exoplanets. So these are the tiniest of motions, because what you have to imagine is that we have a star and a planet. Now, the planet is super light, is not bright, so the dominating light is the star. And the planet is light, so the center of mass is very close to the star. So the star will do a little bit of this wobble. And we need to detect that very tiny wobble. So we cannot do that very far out, but actually we can do it up to maybe a few hundred parsec, or this is several hundred light years, which is actually very far. And of course, if the component that doesn't give light off is a black hole, and this is the star, which is the case with the black hole 3, for example, what you see is nothing here, but you see some star doing a crazy motion like this. And that, of course, is a telltale sign of something very heavy being there, which we cannot see.
Yeah. This was big news last week that Gaia had uncovered a fairly massive black hole, the closest one here in the Milky Way, and the most massive stellar mass black hole.
Yeah, it's the second closest, but
second closest. Okay,
almost as close as the other one. It was also Gaia.
Yeah, and I'm sure that record will be broken at some point.
Sure.
Yeah. So you don't use redshift at all to measure the motion, the proper motion, and the motion towards or away from us at all. It's purely just based on.
Yeah. So, with redshift, you specifically mean radio velocity of the star.
Yeah. Well, or even just, not for the exoplanet side, but just from like when you're measuring, like Hubble famously measured how fast the galaxies are receding based on the redshift of the light. Yeah. And so I guess if the star's motion is constant, you don't really get a big redshift change from the star, right?
Yeah. So redshifts are we see the light spectrum really shift a lot when you go to extragalactic objects, because they recede a lot. The effect is obviously the same, but we indeed measure with Gaia also the radio velocity, which is basically what is called the redshift for these extragalactic objects, which is the motion indeed radially from you. And with Gaia, we have actually also a spectrometer on board, which measures for the brightest stars this radio velocity. And we actually, for example, with Black Hole 3, we could detect it both in astrometry. So we see the motion on the sky, but also we see the radial effect. So we have some very nice plots of the orbit basically being plotted on the sky of the astrometry. And then the radio velocity, which has a specific shape due to the ellipticity of the orbit, follows exactly the pattern that you would expect for this system. So it was a very nice combined measurement where we could validate using the radio velocity independently from the astrometry to validate that it was a correct measurement.
Right.
Yeah.
But the number of stars that you get the photometry for is less than the number of stars that you get, say, just the proper motion for. Like, are you able to measure the chemical signature in every single star that's in the Gaia database, or is there a subset?
Yeah, that's a very good question. So for that, we need to go in a little bit more detail. So because to determine the spectral features, usually we think about taking a spectrum, high resolution spectrum, and then checking the lines and then measuring the abundances of the different elements. Now, the Gaia spectrometer has a high resolution, but it can only work up to magnitude 14 or so, or maybe 16 when you average them. And Gaia goes to 20, 21 or so. So that's really a lot more. But having said so, and also that spectrometer is very limited in range. It is actually built to detect what they call the calcium triplet. And because those are lines that are visible in most of the spectral type stars, so all kinds of types of stars have it, and they are then easy to determine this radio velocity or this redshift, so to say. So there are some other features that can be detected there, which can lead to an abundance or particular elements, but maybe not so many. But what we have in Gaia as well is that we have a red and a blue photometer, we call them. It's somewhere between photometry and spectroscopy, because it's like a prism. So it disperses the light, and we have a resolution of about 60. So it means that from red to blue, you have like only 60 points. So you cannot resolve individual lines or anything, but you can resolve features. And this is actually used to characterize the specificities of the different stars, what kind of type they are, what kind of abundance of elements they might have. So in that sense, we can classify stars, and this data is available up to the faintest magnitudes. Maybe it becomes less useful below magnitude 19 or so. But in principle, these red and blue photometer data, which are just lower in resolution, but therefore you need less photons to basically analyze them, is available in Gaia up for a very large number of sources. So we can actually get a lot of information from that.
So that would let you, say, classify things and go, oh, these are some main sequence stars. These are some white dwarfs. Those are supergiants. And maybe a rough understanding of some of the really bright chemical signatures in those stars, but you're not going to get the kind of sensitivity to say, show me every star that has this absorption line for iron in its atmosphere or whatever.
Exactly. Yeah.
Right.
And
okay.
There's a whole group working in Gaia just to do this, to use all these spectra in detail, to model everything, to figure out for every star the best possible guess we can make of all these things. Yeah.
And I know there are partnerships that the guy works with. There are other surveys that are doing exactly the more detailed spectroscopy, and then you match them up. And now you suddenly get the location, the direction, and the chemical signature of the star. And people have been looking for twins of the sun, try to find our stellar companions from when we were in the nebula, which is really cool. So I've got a sort of a good sense of like the instruments on board, the way the science operations work. And I want to just talk about some of the limits. So, it's 2 billion stars ish. Do you think with a longer survey, like when Gaia Data Release 4 comes out, the spacecraft is still okay, you keep going, do you think there's sort of a theoretical limit that will finally be reached on just how many stars are even feasible to be seen?
Yes, so I think that the 2 billion is sort of, I mean, it's 2.2 or so of stars that Gaia effectively can see. So because there's a whole problem of cross-matching all the individual observations to the same source to identify every transit that we measure, because we have trillions of transits. I mean, it's crazy if you think about the number of observations. So about extending, so the thing is that, so we will not probably get more than this 2 billion from Gaia. Basically, if you want to extend more, you need to, for example, go to near infrared, which we can talk about as well.
I want to talk about that. I've reported on the near Gaia, near IR Gaia IR. Anyway, we'll go into that, and Gaia near. There we go. Yeah, But I want to talk about then sort of this idea of the exoplanet. So one of the big, I don't know, not promises exactly, but one of the really exciting possibilities was that Gaia was going to turn up a lot of exoplanets with astrometry. We've seen some interesting candidates, but we haven't seen the thousands and thousands.
Yes.
Are they in that data, do you think? Will Data Release 4 bring us the deluge of planets?
Yeah, we're working on that right now. And so I can tell you that for sure there will be, I guess, at least hundreds, if not thousands. Also, not only planets, but also brown dwarfs, which are the sort of in-between planets and stars to be expected. Indeed, the predictions that different papers have given is like thousands or tens of thousands of these kind of objects. I think that we will get to maybe thousands or so, hopefully for DR4, at least hundreds for sure. And that maybe we have to wait for DR5 to get to the highest number. And it brings me to the point that you made, like about the length. Because one thing we did not talk about is that the Gaia mission, of course, progressed while we also were processing data and making data releases. And what basically happens is Gaia is still operational, but probably will cease operations next year. So it's not because, well, it has two kinds of consumables. One to keep the spacecraft in orbit, which there is still sufficient as I understand. But the other one is to keep the very precise motion that it's doing to keep the satellite spinning in the right direction, etc. And that's running out. So about slightly more than 10 years of data we will get. Now, the point, of course, is that for every data release, we started with data that was calibrated a bit before, so it was short. So we started at some point with 22, then 33 months. Now, DR4 will be 66, and then the next one will be 120 or so. So we basically double almost every time. And with this doubling, we extend the time range over which we can see stuff. So, for example, just as an example, the Black Hole 3 had an orbit of about 11 years, 11.6, and that's on the upcoming DR4 data. It was a preliminary version, which had roughly half of the time span. So we could see the orbit, half of the orbit, and that was enough for us to confirm it. So every data release, we have more data, which is longer data and better calibrated. So the good thing would be if we would have a way to refuel the satellites to continue it for many more years, just because of when you extend the baseline, you get much more data, especially for finding exoplanets, which we want to find not on orbits of only a few years, maybe tens of years. So the longer you go, the longer you can detect them.
And so that's different from the finding more stars. Like there's just a limit to the sensitivity that Gaia can reach, but with the exoplanets, more time is better.
Yes, yeah. So that's one of the other reasons why we in DR5 probably will have much more, because also, every orbit is basically a validation. I mean, the noise goes down, you are more confident. One of the things, if I can give you detail of the kind of things we don't want to publish. So because the team I was involved with, which actually identified Black Hole 3, is trying to look at things that look anomalous. So if we have an object that looks like a black hole, or actually one of the things we found in the previous data release was many supermassive black holes, supposedly, if we believe the mass. So obviously that was not the case, but then you go back to the data reduction and you find some corner cases. That's, okay, there was an outlier here not taken into account, and then suddenly, high masses are the easy thing, or orbits that look very big are the easy thing that can go wrong if you have an error in some of your data. So in that process, we basically managed to reduce a lot of the systematics that we do in our data processing, and therefore increase the accuracy. And we actually wrote a paper on something called scan angle dependent signals, which sounds extremely technical, but the interesting thing is that because Gaia, as I told you, it's rotating in a certain direction, and the Gaia mirror it doesn't take pictures with a circular telescope. It's like rectangular, which means that it has a high resolution in the direction of the scanning, and a much lower in the other direction. It has basically Hubble kind of resolution. It's like 60 milliarc seconds in the direction of the scan precision. Of measurements on the sky. And the thing is that Gaia, as I told you about how it scans the sky, it has some kind of complex motion, which makes that if you look at a particular star, that sometimes it goes like this, sometimes like that, sometimes like that. So it scans in all kinds of directions. And it's mainly one-dimensional measurements that are used, especially for astrometry. Now, the issue is that if you have a pair of stars which are very close together, and you go in one direction over this pair of stars, that in this direction, I can resolve them because my resolution is high enough to see them. But if I go in this direction, I don't see it. And we found out that in our data reduction analysis, this problem of not knowing when something is seen as a double star and sometimes not, gives a sort of artificial signal, so to say, that makes it appear, first of all, a variable in magnitude. And also in astrometry, it looks like it's wobbling. So it could actually, This was one of the reasons why it looked like some orbits existed, which were spurious, completely spurious.
Right. So,
And
it has better vision in some angles than in
yes,
other angles,
yeah.
and when you finally you have to account for that now in all of the observations. Was this looking at stuff with its good eye or its bad eye?
Yes, yeah, in some way, yes, yeah, and you have to combine them because you use all the data in the end, and so it's another interesting fact. I mean, not many people probably know, but I'm also involved with the variability analysis of Gaia. So we look at variable stars. We try to classify them if it's a Cepheid or if it's a galaxy or a supernova. And one of the things that turn out due to this effect is that because most of the galaxies, if they're far away, I mean, they're hardly ever circular. They have a sort of elliptical core. And almost all the galaxies are having a very nice periodic signal, or not periodic, but a very nice signal as function of scan angle. So they seem to vary in magnitude. Well, in principle, on the sky, they're constant. So with the current data release, we were actually able to classify, because we built classifiers to do this automatically, very good all kinds of galaxies, which was never our goal, because galaxies were the constant stuff, was the stuff we were not so interested in originally. But so it's interesting how this kind of features allow you to detect certain other things or help you, because in another way as well about these close pairs. So these close pairs can be much smaller than the pixel size. So the pixel was like 60 milliarc second or so. So that's 60 thousandths of an arc second, which is the typical atmosphere distortion. And these pairs can be just a few milliarc seconds separated. And in principle, it would be very difficult to detect them even with Gaia. But because of this motion, this gives a specific signal from which you can actually deduce that there is a binary, or maybe not a binary, but two optical pairs. So some can be just in the background or something. So it just gives you another dimension of using the same data to extract information about what we're seeing.
So, you mentioned sort of this galaxies, we know finding black holes, exoplanets, like there's a lot of surprising discoveries made with a survey this vast and sensitive. So what are some other examples of interesting stuff, either, clever ideas by astronomers to look for something, or just weird anomalies that have popped up that are giving you insights into the universe? How has this telescope surprised astronomy beyond just the expected mountains of data about all the stuff that they want to know about?
Yeah. So I think I'm unfortunately not able to follow what everyone is doing with it, but I see that in many fields, just the basis of having distances to stars to calibrate the absolute luminosity of stars and then doing science with that helps in many respects. But I could highlight one thing that was actually part of the design test that they wanted to do, which is with the astrometry. So one of the things is that everyone knows that we are moving around the galaxy in 220 kilometers per second in about 220 million years. But what they actually measured is in a period of, they used only 33 months of data, they could actually see the acceleration of the solar system around the galactic center. So they could measure that it's not going a linear motion of our solar system, but actually it was deviating. And this is an amazing small number. I just looked it up because I just wanted to mention it. It's like 0.2 nanometer per second. Basically, the deviation of our solar system is doing. And over the year, it adds up to about 100 kilometers or so out of the motion around the galaxy. So we have this very tiny angle that we're actually probing, and they could detect this with the Gaia data. And I think these kind of things is just astounding. I mean, everyone had ideas, and it was actually consistent with what we thought it would be. So it, in that sense, was not a big surprise. But just the fact that we can actually measure this with basically a geometric method by using parallaxes and direct measurements of the positions of stars. It's crazy.
Yeah. I mean, I can give you an example. People
please.
were able to make a mass estimate of the Milky Way, calculating the velocity of stars on escape velocities that had been kicked out from supernova explosions or from interactions with the supermassive black hole. And so they looked at, Gaia has turned up these stars. They were able to measure the velocity of these stars and then calculate as they're watching, as they're slowing down, as they're moving away from the Milky Way, to be able to calculate the mass of the Milky Way. And it just came from Gaia. So they got an estimate of the mass of the Milky Way thanks to Gaia data.
Yeah.
And it's
this
kind of stuff. Yeah.
And this is also a very new dimension, this kinematical space that Gaia gives. So with Gaia, we get these proper motions on the sky. We also get for many stars this radial velocity. So we have a 6D phase space. So we have the position and the velocity in 3 dimensions. And with that, you can basically retrace, basically, given that you have a certain potential, you can work out how the stars have been moving over many millions of years and maybe further to trace back what has happened. And what people have found basically in this kinematic data is certain groups and streams which indicate that there have been certain mergers in the past, which is what we expected, of course. But to identify them, and just instead of having just this field of stars, you can say, okay, these 10,000 stars that seem totally random, because of their kinematic properties, they belong to a certain group or stream of stars that come from somewhere else. And for example, for the black hole 3, this is really exciting because so we had the photometry from Gaia, the astrometry from Gaia, the radial velocity, but then also due to the kinematics, it's now expected that there's a stream called ED2. It's a group of stars that are very separated. It's a small group, which might be an old globular cluster, a small globular cluster. So they were all formed together. They have a very small metallicity spread. So they were formed probably from the same primordial gas at some point. If you look at that cluster and you put black hole 3, the new Gaia discovery, it falls smack in the middle. So it's like extremely interesting because that might tell us where it comes from. And the interesting thing is that now black hole 3 is in the disk, but actually it's moving in a halo orbit. So it's actually going around. It just happens to cross now. Maybe that's also why we detect it. It's close enough to us that we can actually measure it properly. And it's also going retrograde. So it's going the other direction than the rest of the stars typically go. So this is a clearly distinct cluster that's moving around. And just having all these measurements, you can actually identify other members of that cluster. And then now people are trying to work out, okay, was it formed maybe, because what's the formation principle? Was it maybe interacting a lot with other stars in the cluster to exchange maybe components to get this binary component? Was it formed like this, or was it maybe ejected? So there's the interesting thing is that Gaia gives you so many clues. It's not just, okay, we see something wobble and it's probably a black hole, but it gives you all these other things that you can then try to puzzle together to figure out what is the history. And it's nice now to follow the different papers that come out on this who try to figure this out. And the interesting thing, some people say, I can explain it with stellar evolution. This binary formed like this and it could survive. The other one said, it's probably much more likely that it was formed in a globular cluster. So it's fascinating.
It must be interesting, though, as a person who works with this data all the time and thinks about the capabilities of the telescope, and then you see someone's proposal for an idea to use the data, and you're like, oh, that's so smart. I never even thought of that. Of course, you could do this.
Yeah. One of the things that's very satisfying, because if you're in the consortium, so to say, we build these catalogs, but we're not supposed to do science with it in the sense that we cannot, this is an interesting object, let's check out what happens. No. After the data release is out, we have the same rights as everyone else. So that's when you can start writing a paper. For Black Hole 3, by the way, we went through a 10-month permission process in Gaia and ESA to get this out before DR4, because we thought it was so significant that we should not withhold this from the community, and they agreed. But so just to let you know that typically we're quite shielded. So for me, it's very nice to be talking openly about all these ideas and science cases that go on. But sometimes we go to these conferences where people have some kind of astronomy hackathon. So you just are together for a week with people who have all these crazy ideas, like what you say, things you never thought about, and they just put something together. And then you can come there they invite people that work in Gaia as well. And then you can help them with the details, because that's what you work on every day. And then like 3-4 papers come out that a few months later are published on all kinds of topics. And that's extremely gratifying and a nice experience to do. So you can really see that the community that's using Gaia is also growing. I mean, people just realize how much potential it has for all kinds of.
I mean, for professional astronomers, like people who are listening to this, how do you get involved in these kinds of hackathon community events? Is there a place where they're announced, or?
Yeah. They're typically just they're actually people from outside of Gaia who organize them and basically ask some of us to join, for example. But these are commonplace events that, if you look at the conferences list that are distributed, people will find them. Yeah.
That's really interesting. So you sort of mentioned that Gaia has a finite time frame. I mean, we're all familiar with Webb's theoretical 10-year lifespan, probably closer to 20 years, thanks to ESA's amazing launch. Perfect launch. Yeah. So do you have a sense when Gaia's last day of science will be?
Yeah, it looks like it might be somewhere beginning of next year.
Oh, no.
Yeah. And that's simply because this... It's the thruster gas, so there's this very delicate, amazing attitude onboard control system, which has been working for 10 years straight. It's a very interesting system in itself. It basically gives micronewton thrusts several times a second to keep the satellite spinning at exactly a specific rate and motion to follow this nominal scanning law that I mentioned before. And this gas, basically, they can see reliably, precisely predict basically when it runs out. And actually, they will reserve a little bit to do some final tests, to do some experiments, because there were a few issues at the beginning of the mission, which we might want to figure out how they work by doing some additional things. And then in the end, it will be shot off in an orbit around the sun. Sort of graveyard orbit where it's supposed not to come close to the Earth for the coming 100 years or so. But the nice thing, it will not crash, so it will be there for prosperity later to fly to with your anti-gravity device in 100 years.
Right.
You can visit Gaia and see some history now. But
so is there like no science that could be done with it just tumbling, like it no longer able to maintain this perfect thing? Like if it's, because I know that like a lot of science gets done where people go, we used all of the in-between time from Hubble. As Hubble was slewing, we grabbed all that data and then we found asteroids or whatever. And so there's just, if it's randomly tumbling, it's still watching. Yeah. So my understanding is that the main issue is that the way the observations are made. So we have CCDs that are fixed, and the satellite is supposed to spin at a certain rate. And what is happening is that the CCD has a certain length, and effectively the star crosses the CCD in exactly 4.4 seconds. And in the CCD, it has like 4,400 pixels. Every millisecond, it shifts the pixels, the electrons from each pixel to the next one at exactly the same rate as the star. This is called time delay integration mode. So it's not like imaging like we're used to, where you take a picture and then you read out, but it's like a continuous shifting readout. And I think the whole focal plane cannot operate in another way, first of all. And I don't think we have any of the design or the mechanics to make it into a pointing mission. So this has been looked at, of course. I mean, any kind of way we can extend the mission has been checked, but unfortunately, Gaia is so specifically designed for this particular purpose of this scanning motion that it will be impossible to operate it any other way. Yeah, I'm such, I always think about these incredible mission extensions, things like what happened with Kepler, where they were, after the reaction wheels died, they still figured out a way to use this thing to discover exoplanets. Or just this week, NASA has been working hard to restore communications with the Voyager spacecraft, which are 47 years old, right? And on like, who knows how to program that anymore? And yet people can figure this kind of stuff out. And so it's always, everyone always says, oh, the lifespan of this mission is 3 years or 5 years or whatever. Mm-hmm. And then they figure out something super clever. But it sounds to me like, no, when it runs out of this gas, it's done.
Originally it was 5 years. We got more than 10 years out of it. So I think we're already quite lucky. that also nothing broke. I mean, we had, when it was launched, it was the biggest focal plane. I mean, we have like about 100 CCDs on board, and it was, and it's been working basically ever since. Nothing really major happened, which is amazing, as well as this thruster onboard control system. We had, I mean, interesting things that happened to Gaia. I mean, unrelated to what you were saying, but it's like micro meteorites. So, because of course Gaia is quite a big object, and so when things hit it, it will move a bit or shake. And because Gaia does astrometry, which is trying to measure the most precise positions of stars on the sky, any of these little hits is actually detectable in the Gaia data. And one of the side products of Gaia is basically that we now know much better the micrometeorite conditions at L2. So I think that has been useful also for other missions that are going there now, because we basically can sort of measure the kind of distribution and the frequency of hits that you might get in that place. And on top of that, there's also the radiation damage. This was actually part of half of my PhD was on characterizing radiation damage before Gaia flew. And what was done, people put this Gaia CCDs in beams at accelerators just to radiate them, to simulate what would happen after 5 years of exposure in space. And it looked quite difficult to calibrate it properly. And what we find now with Gaia is actually that the total accumulated dose, so to say, of damage has been maybe a factor of 10 lower than was originally expected. So that was a really, really good thing, because it simplified a lot of the data analysis. Because it's a bit technical, but in principle, you want to measure, for example, with astrometry, you want to measure the exact position of the star. And Gaia actually measures very little data per star. So typically you get a window around the star, which is maybe 6 or 12 pixels wide and maybe 6 pixels high. And often it's even collapsed in one dimension. So you basically have 12 pixels of points. And what we want to do is we want to find the center of that shape to maybe 100 or 1,000 of a pixel. So you need to know exactly what kind of shape you could expect for these 12 points, align it properly. Now, the whole problem with the radiation damages is that it, as I told you, the electrons are moved every millisecond from one pixel to the next. So you sort of accumulate over 4.4 seconds an image of this 6 or 12 pixels. And what happens if there is these kind of radiation damage causes what we call traps. So basically, they capture an electron and then they release it after a while. Now, what happens if you're building up this shape of the star and it moving over the CCD, and there is somewhere an electron captured on one side and then released on the other side, then you distort the shape. And this gives you an offset, which is easily a tenth of a pixel or much bigger, actually, or comparable to the precision you want to reach. So to model this properly is a huge difficulty. And luckily, so the radiation damage was less. There are also some ways to mitigate this on board that reduce it. So sorry, I'm getting a bit technical, so you should stop me.
No. I mean,
because it's what people normally don't speak about, but it's like it's all contributing to the power of Gaia. If all these things were not designed and thought of and calibrated, it would simply not deliver what people are using in the end. So I'm very passionate about that.
Yeah. So when it does wrap up next year, don't be sad. Be glad that you got an extra 5 years, and that extra 5 years, it was healthy and strong and doing great science right to the end. Okay.
Yeah.
So then, we talked about this earlier, but let's talk about what comes next. So how, because astronomy, like ESA seems pretty committed to having an astrometry mission ongoing as much as possible with Hipparchus, with Gaia. What comes next? Yeah.
So the only real thing on the table is Gaia Near. So this Gaia Near infrared. So I'm not directly myself involved, but as I understand it, it's basically a Gaia-like satellite, very similar principle, also scanning, also doing global astrometry like Gaia, but having detectors that actually are sensitive more towards the near infrared. and it might detect instead of 2 billion, maybe 10 or maybe 20 billion. I don't know. So it goes much deeper. And it would be great if we have that. And one of the main reasons is not only because we can then finally see all these stars also that are hidden from us now behind the dust, etc., which have tons of applications, of course, and very interesting by itself. But one of these other things that people don't talk about a lot is that Gaia has basically set an international celestial reference frame. And what that means is basically it has defined the positions, the proper motions, and the parallax of all these stars. But the issue is that this reference frame, so to know exactly how fast the star is moving and where it is, will degrade when you go further away from the data it was derived from. So as I told you, next year the data will stop. So the best data, the best calibration for any other data that is not global astrometry like Gaia, if you want to use Gaia as a reference, will get basically has a worse reference frame the later the observation or the further away from Gaia observations it is. So all the observations that are made now will be the most accurately calibrated. But if you do observation in 15 years from now, 20 years from now, the proper motions especially will degrade. So you will not have the kind of precision that we have now in terms of in true positions and parallaxes. Now the point is, if you put another mission, Gaia Near, which is hopefully going to fly in 2030, 45, maybe somewhere. Hopefully it will be accepted. This is all speculation, of course. But if it would fly, then you can do a combined solution of Gaia and Gaia Near. And then you have suddenly a much longer span of data. And then you can calibrate all this data in between to a very much better resolution. So it allows you to put everything in that reference grid, which sounds very esoteric, like what do you need this reference grid for? But it has a lot of applications in terms of figuring out how fast things move absolutely in space and also in distance, how they relate to each other. So it is a very important factor, which is not often mentioned, but it would be, if there is no successor, then we will be in a sort of, we were in the highlight of the astrometry for quite a while, I think. And this is crazy to think about because there are so many interesting big missions coming up. But the astrometry itself is something so specific that it's very difficult to do.
So does that infrared wavelength, and you mentioned, see through the gas and dust, see other stars. So you're seeing stuff that maybe is obscured by too much dust farther out into the Milky Way, but it also helps fill in the missing pieces, right? I mean, when I think about Gaia's view and all of those stars, I think about my own view here on Earth. When I look up in the sky and I see all these stars, that is not a representative sample of the Milky Way. That is the bright stars that are tens, if not hundreds of light years away from me, and they're all ridiculously bright. Yeah. Would that increased capability from Gaia Near fill in the gaps in between, or allow you to look farther out into the Milky Way?
Yeah, I think I guess both, but definitely the fill in, because in principle Gaia would have the capability of spotting things in the galactic bulge, for example, much more. I mean, it has the capability of measuring those, but it's simply not able to do so because they are obscured by dust. So if you are able to have Gaia precision on stars that you can actually see at that distance, so it will fill up, I think, exactly as you said, the gaps. There are a lot of gaps in our data. If you look at kind of top level view map of what Gaia has mapped out in the galaxy, there are sort of like these arms which sometimes indicate where there are big blobs of dust basically blocking us to see further, and that will give us a much more complete census. I think there are many more science cases, but definitely also the bulge area and the galactic center are extremely interesting for near infrared observations, of course, and other infrared instruments that are coming online or are online can obviously do these observations and tie their observations to the Gaia grid, which is now very good. So in principle, you can do already a lot of measurements at the moment, but those are usually small angle instruments. So to survey a whole region, it takes a lot of time. Well, this global mission like this Gaia Near would give you, for every star, basically in a sort of uniform way, sampled all this information, much deeper and maybe slightly further away, because some stars are obscured, which are then brighter because you see through the dust. Yeah.
Now you're an astronomer and not necessarily an instrument designer, but do you think about like what would be your perfect astrometry machine if you could, if money was no object? What would sort of take astrometry even beyond, say, Gaia Near to the kind of the next level, do you think?
Yeah, that's a very interesting question. So I've been involved with a mission called NEAT, and later it was called THEA, where we wanted to do, because Gaia does micro-arc second astrometry, or 10 micro-arc second is basically the sort of limit. But if you want to, for example, detect Earth-like planets with astrometry, the kind of signal you need for that is much lower. So for an Earth-like planet, it's about 0.3 micro-arc seconds, the kind of motion around the star. So that's another factor of 100 basically of what we're capable of now. So I would be very interested to see instrumentation that can go even maybe another factor of hundreds with respect to Gaia. The interesting thing is that if you do that, everything becomes variable, because even there might be some stochastic gravitational wave effects that start to play at these kind of levels when you go to really precise measurements. So the other thing I'm also very interested in is like interferometry in space. Like there used to be Darwin, I think now it's called LIFE, but like this constellation of telescopes. Well, I remember in the old days, the Darwin mission was maybe 8-meter telescopes in space, or 4-meter, which combine and could actually image an exoplanet or something. I mean, that would be crazily amazing. So, yeah.
But the like astrometry is, or sorry, like the traditional ways of finding exoplanets, radial velocity and the transit method, they really rely on the planet and the star and us being lined up perfectly so that we can see only the tiny fraction of planets that are passing directly in front of the star or close enough with the radial velocity method. But astrometry offers this hope, and is, that you can see these star systems at every angle, that in fact the best ones are the ones that are not where the star and the planet line up. That you're actually seeing these stars make tiny little circles in the sky as they move, a little spiral. Do you think that there's a way to get at thousands, tens of thousands, hundreds of thousands, millions of exoplanets using astrometry?
Yes. I mean, in principle, it's feasible if we keep on developing and improve our accuracy. So, I mean, maybe an interesting side note to what you said is that because for transits, indeed, you need to be exactly aligned with your field of view. So if the orbits get longer, it becomes very unlikely that a planet will actually cross exactly the disk of the star. Now, with radial velocity, you have more freedom because you measure this direction. But if the star is inclined like this, you will still have a component in your direction, although we have this problem that we cannot, from radial velocity alone, cannot know the inclination. From astrometry, you know the inclination, so that's great. And the other thing is also that astrometry is actually more sensitive to longer orbits, and radial velocity more to closer orbits, because radial velocity is sensitive to the velocity of the star, which if you're closer, they will move faster, and if you go further out, they start to move slower. So it's working the other way around. While astrometry, because of this mass center that's basically causing the star to move around and the planets of whatever you're looking at, the wider they are, I mean, of course, the mass center will proportionally shift, but the orbit will get also wider, and the movement of this system will get wider. So astrometry is more sensitive to longer periods, planets or whatever is orbiting, than radial velocity. So there's a sort of crossover where astrometry will give you actually a sort of complementary sample. And this is where we're hoping to find with Gaia not only a lot more planets, but a whole different zoo of planets, because we can probe out a region which is much further from the host star. The problem is, well, of course, that what I just mentioned, the Earth-like planets, they have a signal which is not detectable with Gaia at all. But things like Jupiter and higher are definitely within our range, and that is why we hope to see at least thousands of planets, at least with Gaia. And for brown dwarfs, I did some estimates. It was like in the tens of thousands, possibly. So yes, if we can build an instrument with infinite money behind, then I'm happy to go on board and come up with something. The other thing is that, of course, the obvious thing, if you want to improve also this is more also the parallax position. So if you want to know distances better to other stars, we can also go to a wider orbit around the sun. So instead of being in orbit around Earth, you take an orbit around Mars or even wider. The problem, of course, becomes that to do one orbit, it takes you many more years. So there's a sort of trade-off if you want to do a mission in your lifetime and get some results.
What about two? What about two installed on either side of the solar system?
Yeah, I think there was once a brainstorm session on this, and actually my PhD supervisor, Lennart Lindegren, he's one of the founders basically of Gaia. I think he had a very clever idea that if you put two instruments and you accelerate them in opposite directions, you can also get from that good astrometry. Of course, there's a limit to which directions is best, but so you could come up with creative ways of improving the kind of measurements.
So you just fly these spacecraft into interstellar space, just in exactly opposite directions into the universe, and the farther they get, the larger the parallax you're able to measure from those two spacecraft.
In principle, yes. Yeah. So
I love it. That's fantastic.
Yeah.
How's that coming?
Yeah, I think we need to write a proposal for that. But that's
that sounds good. That sounds like just the kind of moonshot that ESA is looking for. What are you obsessed with right now?
Well, to be honest, I'm really just I'm really involved with getting all this data for DR4 ready. It sounds very boring, but I'm really invested in getting all the calibrations right and especially finding these planets, because we see now that we can detect them. Of course, the black hole discovery also triggered my interest there. So I would be interested also to pursue that in the future more, to maybe work together with people who do the modeling of how these things can happen, of course, because I'm not an expert on that myself. But I'm involved in many topics, and I just love the way to optimally use the data, so to say. So whatever data it is, to understand where it comes from at first principle, basically, and that's what drives me actually every day. And I feel like I'm privileged, one of those people who got to make their hobby into a job. So yes, I'm very happy where I'm now.
Well, I hope the team knows how excited everybody has been for Gaia so far, and there is a lot of anticipation and excitement for release 4. So keep on going, and we look forward to that next data release. Thank you for your time.
Well, thank you very much.
I hope you enjoyed this interview with Berry Holl. Just absolutely fascinating conversation about the Gaia mission. Now I have thoughts, but first I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Dennis Alberti, Dougie Stewart, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Mark Ansis, Modso, Paul Rohrbach, Stephen Krasaki, Stephen Feiler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. I love Gaia. And I think the reason I like Gaia so much is that I really love surveys. I love large missions that try to capture as much of the sky as possible in different wavelengths, at different depths, and different kind of aspects, and then provide that data in this enormous database that then any astronomer who has a question, who has a theory, wants to look for things, can just pour through that data. That's how you find the motions of thousands of stars moving together through the Milky Way to tell you, oh, something merged in with us. And, a lot of the telescopes that I kind of obsess over, Vera Rubin, Nancy Grace Roman, Euclid, these are surveys, because now it really democratizes astronomy. You don't have to write the perfect paper so that you get access to the telescope, time on James Webb or whatever. You just get good at database programming. You pull the data that you need from the database, and you're able to do science. And this is as available to brand new grads who are coming out of university as it is to seasoned professionals who can still look through the same data. So more interviews are going to be happening on these kinds of topics. So stay tuned for that. Now, I've done plenty of other interviews about surveys that I'm fascinated with, so I'll link a couple of them here. All right, we'll see you next time.